Very good. Well, thanks, Ben, and thanks, Jinshin, for the invitation. I very much appreciate the opportunity to be here and share reminiscences and be part of the celebration of John Dowling. I did my PhD starting in 1987, so I met John around the same time as Barry. I'm not quite contemporary, but from the vintage of my beard, it's pretty darn close. And you know, back in those days, John was at Redstone Arsenal with Chuck Bowden, and you know, had been a postdoc with Marlon Scully. And the quantum optics community was a very small community, and everybody knew everybody. And John was, of course, you couldn't miss him. You know, I'll tell you some stories at maybe the end about John. I want to, you know, maybe celebrate to begin with. You know, John's scientific legacy was important. You know, we joke about John and the way in which he was a character and broke all the rules, but he was also a very important scientist. And one of the ways that I remember early on from John, I think was alluded to earlier. I mean, of course, the title sort of John's spirit rings out in this title. But one of the other things I wanted to say in the context of this paper was this kind of question was only the kind of question that quantum opticians asked. What does it mean to be quantum mechanical? What does it mean to be classical? And you know, when you're shut up and calculate wherever Ben is, you know, physicists say, well, what's the point of that? Well, there was a real point to that. I think there is a real point to that because once we understood what was truly quantum mechanical versus what not, we understood that quantum mechanics had potential resources that we could use beyond what we could do if the world only obeyed classical physics. And so making really challenging where the quantum mechanics was gave us a framework of thought that was critical. So that's where I mean, maybe to answer Ben's question, maybe Bohmian mechanics will give us a framework of thought that will open up new, I'm not necessarily advocating that, but this was the kind of thing that John did and was part of the community that we grew up in, at least we of a certain vintage. The other thing, I recently wrote a review article called Harnessing the Power of the Second Quantum Revolution. And I was interviewed in this paper, this article, it's Symmetry Magazine. It's you can't read it here. It's a journal of Fermi and Slack. So the high energy physicists are discovering, you know, quantum entanglement and the second quantum revolution. And, you know, he asked me, where did the term the second quantum revolution come from? And I was like, I don't remember who, you know, and of course, you know, it's everyone calls, there's books, the second quantum revolution, you know, the Nobel Prize, the second quantum revolution, YouTube videos, what's the second quantum revolution? Of course, duh, you know, it was John Dowling. He was prescient together with Jared Milburn. And, you know, I'm sad that Jared's not here to share with us. Jared's influence and his importance to the whole field, and particularly here in Australia, cannot be understated. Together with John, they really, this was in 2002, I believe. Yeah, 02 is the archive number. You know, they were thinking really ahead, you know, what really defining this. And John was a critical player in helping us to build this framework of thought, which has taken us to where we are today. So I really want to honor that. Okay, one other thing I have to set the record straight on about the famous Squint logo. Those of you who don't know what Squint is Southwest Quantum Information Technology. And it's a workshop conference that started in the late 90s, and John was part of it when he was at the time at JPL. You know, California is the Southwest of the United States, whether they want to think so, at least part of it is. And there was a logo for the first Squint conference in 1999. There was a competition for logo, and one of my students, Shohini Ghosh, put a saguaro cactus inside a ket, and that's from Arizona. Okay, that's the Southwest, but the real truth is that Squint is out of UNM, and we can't have saguaro cactus. But John came up with this logo, and this has been our logo ever since. And what does this logo represent? Well, for those of you who don't know, if you ever come to Albuquerque, and you go to Old Town, you'll see plenty of Cocopelis. It's one of the, cultural appropriations. Unfortunate, we've taken this symbol out of the Hopi nation. And did you have Cocopelli? And there it is. Oh, check them out. And so this is Alice and Bob Cocopelli, and they are playing their flutes. Usually they're the fertility gods, but they're playing their flutes, the song, which is another artifact of Native American culture, the dream catcher. And what's the dream they're catching? Quantum teleportation. And this was a take on, at the time, there's a famous article written by Serge Roche and Raymond, which is called Quantum Computing, Dream or Nightmare, right? And so this was the brilliance of John Dowling, and everybody voted for John's, and it's been our logo ever since. Okay, so what I want to tell you about is harnessing the second quantum revolution in the idea of building a quantum computer, and particularly using a particular technology. And this is some slide, I don't know, I stole this from the internet. Probably, yeah. I shouldn't, thanks, Barry, because it's been buried in my slides for so long, I forgot whom I stole it from. You're a much better man than I. Thank you. There's lots of non-attributing that's going to happen in this talk. I'm sorry. Right. So, here's a few technologies. Interestingly, in this particular one, photons, aren't here anywhere. There's a particular choice of things. But one other technology, so we, got superconductors, ions, silicon, diamond vacancies, topological, Majoranas, God knows. But one of the other technologies that's not here is neutral atoms. And there was an article out of Science magazine back in 2018 that talked about arrays of atoms emerging as a dark horse candidate to power quantum computers. And there are companies out there now trying to build quantum computers or some kind of quantum devices based on trapped neutral atoms. Of course, what's going on in industry stands on the foundation of a lot that's gone on in the academic world. But it started, so here's a photo. This is Shohini Ghosh, who made the saguaro cactus. You recognize this gentleman over here? He's fairly timeless, Gavin Brennan. You never know who that person is, but I'll let you think about it for a little while. Anyway, back in the day, we wrote this paper. It's now the 24th anniversary of the idea of using neutral atoms as a platform for doing quantum computing. Our motivation at the time was the idea, we were really mimicking what was going on in the ion trap community. And in the ion trap community, they were really at this time building the first quantum processors, and neutral atoms had particular potential advantages in scalability because you could get many of them and you can turn interactions on and off. Yeah, Gavin's the guy. There's been a lot of progress in trying to develop this technology over a number of years, over decades now. And I'm not, again, sorry for those other groups whose slides are not here, but there's been a lot of development in that ability. What is it taken? What has enabled us to make progress in this area? Well, I'd say a few things. Firstly, I would argue that the world's most quantum coherent device is an atomic clock. I forgot who gave, I mean, I need to update this now. It should say 10 to the minus 21, no longer, I haven't updated my slides every couple of years. We have to update these slides. But an atomic clock is essentially coherent qubits, right? And that it's based on that coherence that we have this incredible precision by which we can do this kind of frequency standards on which the second is based. But of course, an atomic clock is an ensemble of individual qubits that, don't talk to one another, through which we can't necessarily do quantum logic in the standard form. In fact, one goes to great lengths to avoid interactions between the atoms because that will cause systematic shifts, which would would ruin the precision of the device. Okay, so in order to take this basis of an atomic clock and turn it into a platform that we can use for quantum computing, we need a few more things, a few more pieces of development of technology. One of them is we want to go from the bulk ensemble of many atoms that we look at together to the ability to individually address them. And one of the big developments was the ability to trap an individual atom in an optical tweezer. An optical tweezer is a focused laser beam, and be able to say deterministically, once I know it, I have that one atom, and I can talk to that one atom. And Philippe Grangier really pioneered this in the early 2000s with the fanciest lens that was designed at the Institut d'Optique to make this happen. But later it was determined we can do this with much easier lenses and technology. And moreover, once we have this ability to trap individual atoms and see them, we can rearrange them in arbitrary patterns, be them in 1D, and recent work, particularly out of Misha Lukin's group, and the work out of Antoine Barre's group, following up on Philippe, to arrange atoms into particular arrays in 1, 2, or 3D, even into the Eiffel Tower, of course, if you're going to be in Paris. So that's quite a spectacular development that's happened. I'd say this is really developments, over the last 5 years, to be able to take atoms in these kinds of arrays and put them in places that you want to put them. Okay, so now we can address individual atoms, but we also, if we're going to do quantum logic, we need to interact the atoms with one another. And there are kind of two approaches that people have looked at over the years. One is the idea you can make atoms interact with one another by having the atoms collide with one another. When the atoms physically collide, if their wave functions overlap, then you can get a phase shift on the atom's wave functions that is related to the collision that happens, okay? And that's behind a lot of the work of cold atom physics, particularly in the kind of gas atom microscope that Marcus Greiner and Manuel Bloch and others have been exploring for a number of years. It's a possibility, and people have thought about doing quantum computing based on those kind of collisional phase shifts, but that's a little hard to control exactly what you want to do. Another, of course, atoms are neutral. So you got it, in order to get them to interact, you got to do something. Either you get them at very close range where the van der Waals forces are strong enough, or you can expand that van der Waals force by exciting the atom to a high-lying orbital where at a distance that is almost visible at some micron distance between the two atoms, they feel each other's presence, okay? Physically, fundamentally, it's the electric dipole-dipole interaction, the same one that Gavin looked at in his PhD thesis. But now, potentially with very high-lying orbitals. And this is the physics of Rydberg atoms, which maybe you've heard about, okay? So if I take an atom and I excite the electron in the valence shell from the ground state to a very, very high principal quantum number, we call that a Rydberg state. And when it's in the Rydberg state, well, the radius of the atom, the mean position of the electron relative to the proton, scales like the square of the principal quantum number. Okay, so whereas a standard atom might have, you know, an angstrom scale, if you go to principal quantum number 50, you can have micron size atoms. And when the electron is that far from the nucleus, it's so weakly bound, the atom is so big and fluffy, it's incredibly polarizable. So any nearby atom will affect it. And that kind of dipole-dipole interaction can be at the heart of an entangling interaction between the atoms through which we can do quantum logic. All right, so here's just a rough diagram saying of what the energy, the interaction energy is as a function of the distance between the atoms. Of course, you know, down here at micron scales, there is some force. That's how you would say bind the two atoms together into a molecule. But on this scale, it's negligible. Only when the two atoms are excited into this Rydberg state, which I'm calling little r, do you have a shift in the energy level, okay? All right. So following up a few years later on the paper that Gavin wrote for his PhD thesis was this paper out of this consortium of folks, including Sirac and Zoller and Lukin and Steve Ralston and others, Robin Coté, and Dieter Jasch when he was a PhD student. And their motivation, I know because I talked to Steve for this, was to take the work that Gavin did and say, we want to have faster gates because those dipole-dipole interactions that we looked at were pretty weak. And if we go to the Rydberg states, they could be much stronger. And you can see how you can do quantum logic based on this kind of thing. The idea that they proposed was to say, look, if I thought about this a kind of qubit here, if one atom is in the Rydberg state, then the second atom is blockaded to be excited into that Rydberg state because of this big dipole-dipole shift, okay? That's what's called the Rydberg blockade. And you can see that this kind of interaction, this kind of physics, is the kind of physics that could be used to do conditional logic. Okay, now I'm going to then transition a little bit to tell you about our work in this area. So what fundamentally limits the fidelity of a gate that you can make this way is the finite lifetime of the Rydberg state. The Rydberg state is an excited state, but it's a metastable state compared to low-lying excited states. It lasts for some, you know, few hundred microseconds, depending on the principal quantum number, and that's enough time to do the gate and bring it down. And in fact, it could be made longer if you got rid of black body radiation, because stimulated radiation nearby levels is what really limits the lifetime of the system. There's other technical issues, some of which, you know, we can overcome. And what I want to tell you about is how we might make the best high fidelity entangling gates possible. To date, honestly, no one has made a really good quantum logic gate with neutral atoms. As much as you might hear about hype about neutral atoms, it hasn't happened yet, but it will. It's going to happen. It's going to happen, I think, in the next few years, because now people are beginning to pay attention. Okay, so we're seeking some robust implementations. The way that we're going to do it is the following. So I'm going to step through a little pedagogy here of the physics of how we're going to do this. So let's imagine we have two atoms. For the start, I'll think about those two-level atoms. The ground state is a Rydberg state, and they're separated by some distance, capital R, between the two atoms, okay? Now, for the moment, let's just forget about the interactions between them. And if I imagine that both atoms see the same laser beam with the same amplitude and the same phase, then I can take this two-atom basis and think about the symmetric basis, all right? So there are three symmetric states. You can think about this as the spin triplet, if this was to think about two sort of spin one-half-like particles. So there's the case where one atom is excited. I don't know why Siri's always listening to me. Anyway, where I have one atom excited into the Rydberg state, but I don't know which one it is. We call that the bright state, okay? The anisymmetric case is dark, so I'm not including that one here. And then there's both atoms excited to the Rydberg state. Now, if I have if I turn on the interactions, there's a dipole-dipole shift, which shifts that doubly excited Rydberg state by an amount that can be quite large compared to this Rabi frequency. And by the way, this is square root of 2. That's sometimes known as the superradiant enhancement of that Rabi frequency, okay? And so if the blockade is strong enough, I can ignore the excitation to the double Rydberg state. And you see that I've excited to an entangled state. Okay, so fundamentally, you can see how this is another way in which the dipole blockade or the Rydberg blockade leads to entanglement between the two atoms. That's one way to see it. Now, we're going to use this in a particular way. And Barry mentioned dress states in his talk about Outlier towns and the verboten AC Stark shift. But it is the AC Stark shift. The Stark shift, you'll remember, is the shift, whether it's canceled in culture or not, is the shift that you get in the energy level due to an electric field. And this is the shift. I know, maybe is it me who's doing that? No. Yeah, God is striking me. Yeah, what's my grandmother? Sorry. She knew I was using a Nazi's name, I'd be. Anyway, excuse me. So, right. So the AC Stark shift, or the light shift, which we'll use a much better term, the light shift is the shift of the energy level of an atom due to the light that is applied to it, okay? And the way we can think about that is in perturbation theory. If I put the light on, there's a perturbation to these states, which I get by just diagonalizing the Hamiltonian, including the interaction of the atom with the lasers. And the dress states, which are the perturbed states, the new eigenstates are superpositions, or what is sometimes called admixtures of the bare states, okay? And the amount of superposing or admixture depends on the detuning, how far off from resonance, and it depends on the Rabi frequency. That's to say, the coupling between the atom and the laser, okay? And if I were to look at what these energy eigenshifts are, the light shift as a function of the detuning from resonance, then I get this avoided crossing, okay? This is in the so-called rotating frame, where the two energy levels are looked into in the reference frame at which the laser beam is oscillating. And this kind of diagram, what you see is if I were to chirp the laser, say all the way I started far below resonance, that's on the red side of resonance, I'm in the ground state, and I chirp I would go through to an equal superposition of ground and Rydberg, and then eventually sweep to the Rydberg state. That's known as adiabatic passage. It's one way in which I could transfer the system from the ground state to the Rydberg state. And if I started on the blue, I would chirp that way. Okay, now, let's say I do the same thing, but with two atoms, okay? So now, with a perfect blockade. So now I'm going to dress this ground state, two atoms in the ground state, I'm going to dress them with one atom excited into the Rydberg state. However, it's in this entangled state. I don't know which atom. So I am admixing the ground state with some Rydberg character. But the way I'm doing that is I'm admixing in some of this entangled state into the system, okay? And I will get the same kind of diagram, this avoided crossing diagram that I had, but this avoided crossing diagram is different than I would have if the atoms didn't interact. Then I would get this diagram, which is the dotted line, which this splitting would be twice the Rabi frequency as opposed to the square root of 2, the Rabi frequency. And the deficit, the difference in the light shift that I get for the interacting atoms compared to the light shift for the non-interacting atoms is the entangling energy of the dress states. I mean, there's layers upon layers here. The point here is that by using this dressing protocol, we're able to take the Rydberg character and put it into the ground states where it's much more controllable, as we'll see, and will give us a robust way to make entangling gates. Now, I know I'm using up a ton of my time because I'm a slow speaker. How much time do I have, Chair? Oh, geez. Okay. All right, thank you. Anyway, we'll go. I'll speed up a little bit, and I'll skip one part, and you can ask me questions at the end. Okay, so an experiment was done to see this effect with my collaborators at Sandia National Labs in Albuquerque back in 2016. And in this case, this was a cesium atom. This is the ground state. It's the F equals 4, M equals 0 clock state of cesium. And it was with a UV laser up to N equals 64 dressing that state, okay? So that shifts this level. Now, what we see now is that by doing this dressing, we can turn the blockade physics, which was seen in the optics, and turn it into blockade physics with microwaves. And that's a good thing because microwaves are much easier to control the phase of and all the other stuff than with lasers. And so what we looked at is what we call the spin flip blockade. What's the spin? This is the spin of the electron and nucleus of the atom. This is my qubit. This is the clock state, and there's a, whatever, 10 gigahertz microwave that can flip the spin from 0 to 1. But the point is that because of this light shift, this deficit, flipping one spin gives me a shift, but flipping two spins, I'm too far off resonance. So by using the dress states, we've turned the dipole blockade for an optical photon into a spin flip blockade, and we can manipulate the spins of the atoms rather than the orbitals, which is much harder to do. So this was observed in this experiment, and Bell states were made. We now want to turn this into a gate. Okay, so I'm going to go through how do we do that. Oh boy, I'm going the wrong way. How do I go back? Sorry. All right, so how are we going to turn this into a gate? The way we're going to turn this into a gate is just through that same adiabatic passage that I described earlier. So the idea is, here are my logical basis states. And I'm going to chirp the lasers, amplitude and frequency, so that I move on one of these adiabatic curves. And as I move on one of these adiabatic curves, I pick up a phase that depends on the light shift. Either I pick up the light shift associated with only one atom being dressed, or I pick up the light shift associated with two atoms being dressed. And because there is a difference between the two atom phase and the one atom phase that depends on this entangling part of the interaction, I can create a entangling gate. And in fact, this method is very robust because generally speaking, adiabatic passage doesn't depend on exactly, the pulse sequence. It's just that you have to be slow enough to be adiabatic and pick up the right phase. It's not a geometric phase. This is a dynamical phase. It's not like a holonomic, topologically protected kind of thing. It's dynamical phase done adiabatically. Okay, and when you can put this in the context of you can sandwich it in a kind of Ramsey interferometer, if you're familiar with that, which will be a spin echo that can cancel out any excess noise phase that are associated with the single atoms. So this is a very robust technique. It's used all the time in atomic physics, and we can get quite very, very high fidelity gates in principle. Now, this experiment was done at Sandia a few years ago, and they didn't see those fidelities. They saw fidelities that were substantially lower. We don't still know exactly why, except probably there was some phase noise that was not common in two parts of the interferometer, so the spin echo didn't cancel out the noise. And well, that's a technical problem, and we'll have to see whether we can get beyond that. Okay, I think I'm running out of time, so I'm going to skip this and just, I want to get to this last slide here and just some parting thoughts. So Scott Aronson, as many of you know, has a very popular blog, and after John died, he had a testimonial to John and opened it up. So I just wanted to share with you the thoughts that I wrote then, because they still feel them now after John's passing. So I'll just read it aloud here. The news of John Dowling's passing was a shock to the system. I had known John since I was an itty-bitty graduate student in the late 1980s, as the quantum optics community was small and intimate. But even if it had been a giant community, you couldn't miss John. He was loud, bombastic, and impossible to ignore. He wanted it that way, and so did everyone around him. He was a provocateur, and his provocations always pushed us to think harder while we simultaneously dueled with him. Always a good spirit, but always pushing the limits. But here's something that I was reminded of in the recent Wang et al. Comment. So one particular story I'll always remember is back in the early days of quantum computing in the 1990s, I was giving a talk that I like to call the Tao of quantum computing, okay? The point of that was that coherence and decoherence were two sides of the same coin, two sides of the same fruit. In discussing this, I said, so let's talk about the green side of my yin-yang. But John heard the green side of my yin-yang, which has a very different meaning. And he jumped up and said, what does your yin-yang have to do with it? And he and Chris Fuchs burst out into laughter. I never saw that slide the same way again. So goodbye, John. We'll miss the color you brought to our community, the laughter you invoked, the way you challenged us to root out the bullshit in quantum information science and life in general. Give them hell wherever you are.
Thanks, Ivan. We can take a few questions if we have some.
Barry,
Start with Barry.
Yeah. Yep. They are. It is.
Is your argument then that the adiabatic method will deliver?
I do. Well, what I think will deliver is the dressing protocol, because I believe, so what is really limiting the infidelity of the gates? There's, in my opinion, two real technical problems. The problem of phase noise on lasers, and the problem of the fact that the atoms aren't infinitely cold. And so the motion of the atoms plays a large role because the distance between the atoms varies and the strength of the shift to vary. But more importantly, if you have a protocol which requires you to do a particular rotation on the Bloch sphere, it depends on the Rabi frequency and the detuning of that laser to make the proper trajectory to pick up the proper phase. And that's what's limiting the gates. For example, the so-called LP gate, Levin-Pichler gate, which is the most popular gate right now out of Misha Lukin's group, had a fidelity of, 97%, say. And it was really limited by atomic motion and laser noise. I think by taking the protocols, mapping all the physics, we can do an LP gate, but do it with Raman or microwave rather than optically. You win in two ways. You win because you have no Doppler. Your wavelength is huge in that case. So, the K times V, the Doppler shift, is negligible. The other thing is there's no noise equivalent. I mean, being able to control things in the RF microwave compared to the optical is much stronger. So I think that's really, it's not necessarily the adiabatic, whether that's going to work or not, I think remains to be seen. But I am bullish on the idea of using dressing as the way to go, as opposed to direct excitation. Andrew, do you have a question? Yeah. Yeah, no is the answer. I mean, I worked with a few different experiments. There's a recent experiment. Well, I know in those experiments, Mike Martin, who was a postdoc at the time, and whom I work with, he's at Los Alamos now. I mean, that paper has not been published because he was never able, to his satisfaction, understand the gap between the measurement and what they calculate to be the error budget. There's a huge gap, and no experiment, to my knowledge, has met that gap. I don't know why. There was a recent experiment from Adam Kaufman's group that I think might have had it close, but to my knowledge, no. I don't think they understand where all the noise is. Right. It does, but it comes it moves over. So there are two things. One is, if you can do things farther off resonance, then the noise matters less. And the way it comes in is a kind of second order effect. So in the same way that if you do the Rydberg blockade, the entanglement doesn't depend on what the strength of the interaction is, as long as it's big compared to the Rabi frequency. So if the dipole-dipole shift is big compared to the Rabi frequency, I don't care what V is. In a similar spirit here, I don't care what this kappa is, as long as it's big. So what the laser value, what the value of the dressing strength is, doesn't matter, at least for making the Bell states, okay? Well, okay, so you're right, this is under the idea of a symmetric, that both atoms see the same laser and so forth. And, you know, the degree to which we can design around robustness, how much robust control can we do? I mean, composite pulses and, you know, the whole optimal control kind of thing, which, you know, we worked on, for example, with Pol, it makes a big difference. But you need to be able to do that kind of composite pulses or robust control, you need to have the base interaction be very good, right? So I need to be able to say, have a waveform where the phase of the microwaves is well defined over the course of something. And that's why I'm optimistic about using the microwaves, because I think we can employ more of the tools of robust control in a reliable way than we would be able to do with UV lasers. That's the overall argument.